Okay, welcome to STAT 313 lecture 17. So today we'll be discussing how to infer things about the generalized linear model. In particular, we'll be studying this in this section. So we'll be starting with ANOVA, one-way ANOVA, and then we'll slowly progress towards two-way ANOVA, and we'll do a lot of things related to that. So this is the last topic for this course, so let's get started. Now, before doing that, since we need some sort of background from the F distribution, so let me just mention it at the very beginning and then we'll move on. So here is the name of this particular chapter that we are starting today. So this is called Inferences about normal linear model. So that's what we're going to study. And we'll be starting the study by the analysis of variance. But before doing that, so let me remind you that I don't like you should have seen this before in the previous course, but if you did not see it, so let's mention this here. So suppose we define two for two independent chi-squared random variables. Let's name it U and V, and where maybe the degrees of freedom is R1, df is the degrees of freedom is R1 for U, and suppose for V, the degrees of freedom is R2. Okay. The a quantity W, so we define W, which is given by U over R1, V over R2. Okay. Now, it's known that this distribution is called the F distribution. So let's write it down. It has a distribution. It's a pretty messy expression, but let me just write it. The distribution for W is given by GW, which is equal to, once again, it's a longer expression. So it's R1 plus R2 over 2 in gamma, and then R1 over R2 over R1 over 2, and then we divide by gamma of R1 over 2, gamma of R2 over 2, and then W to the R1 over 2 minus 1, and in denominator we have 1 plus R1 W over R2 to the power of R1 plus R2 over 2. So it's pretty messy expression, as I mentioned. It's 0 less than W less than infinity and 0 elsewhere. So this is the distribution. So the PDF for W. So this is usually referred to as it is called an F distribution. Okay. And we also write this W as F. So, and we write F is U over R1 over V over R2. So the thing to remember is U and V are independent chi-square. U has degrees of freedom R1, V has degrees of freedom R2. So then this quantity is called F distribution. There are two parameters. So this is aside one, meaning that it does not have any relation to what we're going to do. I mean, it doesn't have any direct relation other than being a background material. Okay. I'll write another aside. So I'll call it aside 2. And this is something I wrote before. But it's long time. I think during the first lecture or the second lecture, we mentioned it. So let's write this. It's called the student's theorem. It's called the student's theorem. I think during the first lecture, we mentioned it, but it will be pertinent today. So let me just write it down. So it goes like this. Let x1, x2, xn be IID random variables each having a normal distribution. So that's important. So we are assuming that x1, x2, everything, they are having the normal distribution with the mean equals to mu and variance equals sigma squared. Okay. Now define a new random variable, the sample mean, which is 1 over n summation xi, I from 1 to n, and then the sample variance, which is given by 1 over n minus 1 summation I from 1 to n xi minus x bar squared. So that's the sample mean and sample variance, right? Then the conclusion is, there are 4 conclusions. Number 1 is x bar. It follows a normal distribution with mean mu and variance sigma squared over n. It's easy to prove. Number 2 is x bar and s squared are independent. We'll be using this fact today. I will be needing this. Number 3 is n minus 1 s squared over sigma squared. What is this quantity? So n minus 1 s squared is basically this sum, right? So n minus 1 s squared, and I divide it by the sample variance. So s squared, sorry, I divide it with the population variance. Sigma squared is a population variance, s squared is a sample variance, right? So this has a chi-square distribution with n minus 1 degrees of freedom. That's the third part. We'll be also using this today. And the last one is the random variable t, which is given by x bar minus mu over s over square root of n. It follows t distribution with n minus 1 degrees of freedom. Will not use that uses that much. We used it before, remember? So today, for today's purpose, this and this will be the most crucial one. So we have actually used this a lot when in the second chapter, or when we study chapter 4. So there we use this one, and we use this for a lot of hypothesis testing. Okay, but today we'll be focusing on this one. Okay, so that's our aside 2. Now let's come to the main point. So with this, we are now ready to talk about the topic, which is a very famous one, called one-way ANOVA. The term ANOVA is this really means analysis of variance. In short, there it's called ANOVA. So this is a concept that was developed by, in general, ANOVA was developed by the very famous statistician Fisher, R.A. Fisher. You have already encountered his name when we studied the Fisher information in connection to that Rao-Kramer lower bound. Okay. So let's start with an example. So suppose, what's the deal here? Suppose that there are 3 machines in a factory. For producing say an iPhone chip. So there are 3 machines. So 1, 2, and 3. All right. So this machines are operated by 3 different persons. Okay. So these machines are operated by operated by 3 different persons. So this is my machine 1, machine 2, machine 3. Okay. Now, suppose this, what's the deal? So sample chips. So they're producing a bunch of chips. Now sample iPhone chips produced by each machine are collected and say, and their weights are measured, say, or any parameters are measured and their, say, weights are measured. Okay. So there are a bunch of chips here. So the samples are these are the samples. So we are taking the samples and then these are measured. Okay. Now, of course, in general, and this is expected, the weights. By the way, I'm assuming a manual machine. Okay, so it's not really computer, like a manual procedure. So basically, a person is making this chips. So of course, even if it's made from the same chip, same machine, the chips will have some different weights, right? The weights, they'll vary very small, but it'll be different. The weights of each chip, of all the chips, will not be the same, right? So what is the source of variation? So source of variation can be due to machine, which machine you're preparing this on, or it can be due to the operator. Meaning that even if you're producing from same machine one, so each chip will be different because ingredients will be, if it's not mixed properly, maybe the first chip will have some weight and second chip will have a different weight and so on. Okay, so because the operator will need to uh, provide the ingredients. So depending on the ingredients, the machine will produce. So basically, due to the operator, there will be, so if I'm fixing our attention to machine one, and if the operator, so operator one is operating machine one, then the variation of the weights of these chips are not due to machine because they're produced on the same machine, but they're due to the operator. Versus, I mean, if we have two different machines, and if we pick up two balls from here and here, so there are two sources of variations. So one is, first of all, they're produced from different machines, and also they are produced by different operators. So there are two sources of variations, right? Okay. The question is, with this help, or with the help of, so the question we are trying to answer is the average weight produced by, say, machine one, machine two, and machine three, is the average weight the same? So here's the question. Is the average weight produced by machine one, machine two, and machine three are the same? So now this kind of questions will be trying to remember that, I mean, when we are doing a hypothesis testing, we have to sort of consider both the facts. First of all, so we'll be seeing that how these average weights are distributed, and what is that in comparison to the each machine, and what is that in comparison to for the same machine when, so it's basically operator specific error. Okay, so we'll see all these things in this section. So let's see. So now so this problem, I'll be writing this in terms of some mathematical notation. So let's get started. I will be generalizing this problem, and that is called the one-way ANOVA. Okay, so consider some formulation. And actually we'll be discussing a general formulation. So consider B number of independent random variables with unknown means mu1, mu2, mu sub b, respectively. In the last example, once again, you can think that there are three buckets, but there is nothing we can, nothing to prevent us from having more buckets. So suppose we have maybe the first experiment is for machine one, second experiment for machine two, third experiment for machine three, and we have B number of machines. And the average weight or average unknown weight here is mu1, here it's mu2, and here's mu sub b. That is the actual average weight. Okay, it's not the observed weight. So that's the sample mean. Assume, here is an assumption. Assume that the weights, or assume that the random variables, in our case the weights, have a common but unknown variance equals to sigma square. So that means we are not assuming that each of these will have various kind of variances. Say, suppose it can very well be the fact that it has mu1 sigma 1 squared, mu2 sigma 2 squared, and mu sub b sigma b squared, but we are assuming all the sigma squared are the same. So all the variances here are the same. So that's our assumption. Now we can let mu x sub 1, x sub 2, that's the third one, and then x sub so we have now two sources of variation. So let's write x of 1 comma j, or 1j, x of 2j, x of n sub j. I'll explain what it means. So it's x 1j, 2j, and n sub j represent a random sample of size nj from the normal distribution with mean mu sub j and variance sigma squared. Okay, let me just specify, let me just focus on this one. So what we are really saying is, what are this? So what are these random samples? So suppose we have a bucket, so as I have drawn before, but now I'll be just focusing on the bucket number m sub j. Okay, so there's m1, m2, m3 up to mb. So there are so many buckets. Now suppose I'm thinking of the machine m sub j. Okay. Now from here we have various variables. So we have x1, and just to characterize that it's from the jth bucket, so I write x1j. Then we have x2j, x3j, and finally the last one is x of njj. So how many elements are here? So number of elements or number of samples equals to n sub j, right? So it's 1, 2, 3 all the way up to n sub j. So that really gives me the number of samples for the jth bucket, and I'm talking about this one. Okay. So I'm talking about the random samples of size nj from the and we are assuming that they are from normal distribution with mean mu sub j. Remember, so we assume that so this one has mu1, mu2, mu3, mu of b. So for the jth case, it has the mean mu sub j and variance sigma square. So that's the setup. And now we can use the notation. So suppose I'm talking about the first one, so it should be x11, x21, x31, and xn11. So where n1 is the total number here. So I'm assuming that this has again m1, it has total n1 sample. m2, it has total m2 sample. mj, it has total n sub j sample. and so on. Okay. Now, a good model for this one, on an appropriate model. So here's a model, an approximate model for this one can be given by x of ij. Once again, what does these two numbers mean? The second number is from which bucket you're talking about, like you're considering. So think about our example for the machine. So this is J, stands for the machine, and I is the which sample for that jth bucket we are talking about. So for example, you're talking about the ith one. Now a model can be written as it's given by, say, mu sub j plus some error term, right? So plus some error terms, which I write as eij, and where this I is the number of elements for the jth bucket. So I equals to 1, 2, up to nj. And j is there are b number of buckets. So remember, this is m sub b. So j is 1, 2, up to b. I know that it's a little confusing in terms of notations, but it's not really hard. Okay. And what is this one? Where this eij is assumed to be, so there are IID and with normal 0 sigma square. Okay. That's a common error term. So for instance, so the weight of the chips in this bucket or in this machine is given by the average weight plus some error term, right? So this is a random variable, which is the error term, which is giving me at the approximate. So the error is from 0 sigma square. Okay. Now, once again, this is just a model. So a model gives me the mean plus some error, and the error is from some normal distribution with zero mean and variance sigma square. Why variance sigma square? Because now if I compute the variance of for variance of xij, then this will be sigma square, which is what is known. We have seen that, assume that the random variables have the common unknown variance sigma square. So this agrees with what we wrote before. Okay, that's it. That's just the setup. And one more notation, and I know that it's a lot of notations, but let me just write one more notation. So let n be equal to, so there are, so n1 here, nj here. So for the second bucket, there are n2 elements. For the third bucket, so the n3 and so on. So the total number of n is given by j from 1 to b n sub j. Okay, so it's the total sample size. With this in mind, now we are ready to define the hypothesis. So now let's, after all these notations, we desire to test what I wrote at the very first page, H0, that if all the population means are the same, versus H1, that at least two of these are different. Okay, so this is another way to write this as mu j is not equal to mu j prime for some j is not equal to j prime. So that means at least two population means corresponding to two different class. I hate to write this population mean. It means from those two different classes. Okay, means from two different classes, different groups are different. So for instance, so maybe the mean for the M1 is different from mean for the M2 or so on. Any two is different. So that's ideal. Okay. Now, first of all, this one, there are two different ways of computing this. One way is, I'll be showing a little theoretical way, so bear with me. And then we'll be doing some examples. All right, so let's see. First of all, I'll be using some notations. So the likelihood function, so there are two different things. So first of all, I will call it full model parameter space, which will denote by omega, which is equal to mu1, mu2, mu b sigma squared, such that this mu j is any number and sigma squared is positive. Okay. So that's the full model parameter space. Because so these are the almost all these are values of the parameters. Okay. And then we'll call the reduced model. What does it mean? It means that under the full model under H0 parameter space. What does it mean? So it really means that under the null hypothesis, all these mu's are equal, right? So we'll be using that. So we'll be using that. This is I'll write this as little omega. So this is once again mu1, mu2, mu b, and sigma squared, but all my mu's are equal. Mu2, mu b, and we call it mu. And then there is sigma squared. So that's my reduced model, or under the null hypothesis is true. Under the null hypothesis, we assume that all the for different groups, the means are the same. Right? So so let's write this down more clearly. So we have the first bucket, which has x11, x21, x31, all the way up to xn11. Okay, so there's a total is n1, and I have mu1 sigma squared. The second one has a sample x12, x22, x32, and the last one is xn22. Here the total is n2, and it follows mu2 sigma squared. And the last one in this list is x1b, x2b, x3b, all the way up to xnbb. Okay. Here the total is n sub b, and it follows a normal distribution with mu sub b sigma squared. Okay. Now let's consider the likelihood function. Likelihood function for the full model. Okay, it's given by L of omega. Let's call this L of omega, which is given by, let's see. So let's write it for ijth element. So ijth element means 1 over, so let's focus on xij. Okay. So I have 1 over 2 pi sigma squared to the 1/2 e to the minus 1/2 xij. Now if it's xij, so that means it must be from the jth bucket, so it has the mean mu j. So it's mu j over sigma squared, right? Okay. Now for the, so how many i's are there for the jth bucket? So there are n sub j i's, right? So I is 1 to n sub j. And now finally, I have how many j's are there then? So j's are really from 1 to b. So that's the total likelihood function. Okay. If I simplify this, so the total terms is n. So grand total is n. Remember that n I from 1 to b is n. So that's the total. So I can write this as 1 over 2 pi sigma squared n over 2. And then this one is simplified to exp and minus, so this 1 over 2 sigma squared. And this product becomes summation. So summation I from 1 to n sub j, j from 1 to b. And then we have x of ij minus mu sub j squared. Okay. So that is the likelihood function for the full model, meaning that when we assume, when we did not really assume the null hypothesis. Okay. For the reduced model, that means that under H0, when we assume that all the means are the same, what do you have? So we can write this L of omega. So all we know is now all the mu's j's are same mu, right? So I'll write the same thing, 1 over 2 pi sigma squared n over 2 e to the power of 1 minus 1 over 2 sigma squared summation j from 1 to b summation I from 1 to n sub j xij. The only change is now I have mu. Okay, instead of here, this is the key, here, this is the key. So for the reduced model, we have mu, and for the full model, we have this one. All right, so this is the likelihood function under the null hypothesis. Okay. So this, what we wrote here, so this is just one sample model with sample size equals to n from a normal distribution mean mu sigma square, isn't it? So I can imagine this, that I have this value. So x11, x21, x31, xn11, x2, x12, x22, x32, xn22, so on up to x1b, x2b, x3b, up to xnbb. Okay, what is the total? So here the total is n samples. That's the sample size. And where are they from? So they are from, we assume that so everything has the mean mu, right? So all the like for each bucket the mean is mu. So that means for every sample the mean is mu. So each individual sample is drawn from some certain mu, right? And variance sigma square we already assume that's true. So that means I can just think this. It's a giant draw. By giant, I mean, so n number of draws from a normal distribution. Now, from this, we already know how to find or what is the maximum likelihood estimate for this mu and for this sigma squared. So we know this. So we have seen that we have computed the maximum likelihood estimate for such cases before. It's basically normal distribution, right? And what we found is we can find that mu hat in this case would be basically the average of all these. And how do you compute the average? And now we have a double sum because we have two indices, but otherwise it's very simple. 1 over n, j from 1 to b, and then I from 1 to n sub j, xij, which we'll denote as, say, x bar. And sigma squared, which is equal to 1 over n, j from 1 to b, I from 1 to n sub j, xij minus x bar squared. So this has another name. It's called the grand mean of the sample. So, I mean, the way it's meaning that you have different groups, and each group you have different elements. It's a grand mean. That means it's a mean of everything. Okay. Okay. Now, so if we evaluate the previous one, namely this one, LW, L of omega, if we evaluate this L of omega at this MLEs, at the MLEs, maximum likelihood estimates, we obtain. So what do you have to do? So basically, I have to replace this mu by x bar and sigma squared by what we just wrote. Okay. Now, if you did that, if you simplify this a little bit, you can easily check that, if I just write, instead of mu, if I write x bar, then this quantity is basically 0, isn't it? Let's consider this. So j from 1 to b, I from 1 to nj, xij minus x bar. Let's compute this as an aside. So this is going to be summation j from 1 to b, summation I from 1 to nj, xij minus, this is summation j from 1 to b, summation I from 1 to n sub j, x bar. This by definition is n times x bar, according to our definition of x bar. So x bar equals to this one. So n times x bar is this sum. Minus, and there are total n amount of elements. So this is n of x bar, right? Note that. By the way, again, let me remind you. So n is really n1 plus n2 up to n of b. So that's what my n is. It's coming from the sum. Total number of elements times x bar, so it's a 0. So this quantity is 0. So if we obtain, or if we try to evaluate the L of omega at these two MLEs, so that means x bar and at this one, so what we'll have is L of omega would be equal to 1 over 2 pi sigma hat squared over n over 2. And then the exponential term is basically, so e to the minus 1 over 2 sigma squared And then we have basically summation, and then we have summation, double summation, j from 1 to b, I from 1 to n sub j, and then we have x sub ij minus x bar squared, right? Now look at this one. What is this? So this quantity is nothing but n sigma hat squared, isn't it? Also, I should have sigma hat here. So then if I simplify this, I have just 1 over 2 pi sigma hat squared over n over 2 e to the, so this becomes minus n over 2. Okay, so this is when I evaluate L omega at the maximum likelihood estimate, and let's write this as omega hat. So its omega hat is when the MLE are used for computation. And that is what we get. Now, let's consider now the full model. So when we consider the full model, if we now have the full model, for the full model, we have already written the log likelihood function right here, the likelihood function right here. So I can simplify this by taking log of L omega, which is equal to minus n over 2 log of 2 pi minus n over 2 log of sigma squared minus 1 over 2 sigma squared j from 1 to b, I from 1 to n sub j, xij minus mu sub j squared. We have seen this. I mean, I'm just taking the logarithm of something that we already computed. I mean, this expression. So I'm taking this expression and I'm taking the logarithm of that. All right. So so basically I have to maximize this, and I'll not how do you maximize this quantity? So we have to, so we have variables. So here need to maximize this. This with respect to, say, mu1, mu2, all the way up to mu b for the full model, because they're not the same, right? So what we need to compute is, we have to compute the partial of log of L omega over partial of mu of j, and you can check it's going to be 1 over sigma squared, and so this is going to be I from 1 to n sub j, and then xij minus mu j. Okay, note that I'm differentiating with respect to mu sub j, so only the terms of mu j would survive, because the other terms, so if we have the other term, which is right here, so there are other terms. So if this j is different, so suppose this j is say k, when I differentiate with partially with respect to mu j, it's 0. Okay, other terms for, say, mu I which is not equal to mu j. I'm talking about this one, x minus xij minus mu I, where mu I is not equal to mu j, will be 0 when you take the partial. Okay. And now if I set this partial to 0, if I set this to 0, this will give me the estimate for mu j hat as 1 over n sub j summation xij and I from 1 to n sub j, okay, which will denote as x bar j. That's our notation. So here j equals to 1, 2 up to b. Once again, what is this quantity? So for instance, if I give you this one, so here, if I want to compute, say, x2 bar, x2 bar. So x2 bar would be the sum of all this divided by n2. What is x1 bar? X1 bar, it would be, so x1 bar would be x11 plus x21 plus xn11 over n1. x2 bar would be x12 plus x22 plus xn22 over n2, and so on. Yep. So this is the, and we can show that this is actually the max. And also, this derivative does not depend on sigma. To find the MLE of sigma, we substitute we substitute mu sub j by mu sub j hat, which is xj bar. And let's write this. This d of log of L omega over d of sigma would be equal to, you can check, it's minus n over 2 to sigma over sigma squared plus 1 over sigma cubed j from 1 to b, I from 1 to n sub j, xij minus xj bar squared. Okay. And thus we found, after a simplification, so sigma hat squared in omega, which is 1 over n, after setting this to 0 and computing this, so it's I, so j from 1 to b, I from 1 to n sub j, xij minus x bar squared. All right, so we found the maximum likelihood estimators for this case, for the full model. Okay, so hence, so substituting these MLEs for their respective parameters, in L omega, we get L omega hat. So this was the L omega, the full model. So what we are doing is we are just replacing this mu by the quantity that we found, and that sigma squared by the quantity that we just implemented. So it's going to be 1 over 2 pi sigma omega hat squared to the n over 2. And then we get the same way we have done before. So it's essentially, let's write this down. So it's exp 1 over 2 sigma omega squared. And then I write j from 1 to b, I from 1 to n sub j, xij. And now I'll be replacing mu sub j by mu j hat squared. Okay. And mu j hat is what we found as right here, xj bar. This is really xj bar. And according to our definition of this sigma, this is really with this notation. So this is n times sigma omega square hat. Okay. So just like before, it's 1 over 2 pi sigma omega hat squared over n over 2. And this is e to the power. So it's n or minus n over 2. Let's now label this. So we have computed L of omega hat before. So let's call this 1. And let's call this 2. By the way, here omega hat means the same thing when maximum likelihood estimators are used. Okay. Now we can do a ratio test, or the likelihood ratio test. Okay. Hence, now we are ready for our analysis. Hence, the likelihood ratio test rejects H0. In H0 was all the means the same in favor of H1 for small values, as we have seen before, of the statistic gamma hat, which is given by, say, L of omega hat over L of big omega hat. So remember, this is for the null hypothesis, and this is for the general case. Okay. So if this is a very small value, so that means more than likely that the likelihood function for the case when the model parameters are the same, the means are the same, are not, it's not true. Okay. So now let's compute this. So basically, what is that? This quantity, and this really means so the first one we have already computed in 1. So it's essentially 1 over 2 pi sigma hat squared n over 2 e to the minus n over 2 divided by what we just found, 1 over 2 pi sigma omega squared n over 2 e to the minus n over 2 by 1 and 2. So essentially, this is same as sigma omega squared hat over sigma squared to the power of n over 2. Right? Okay, so we want to have some small values for this quantity. Now, another way to, this is fine. So, or some large values for, you see this constant. So we are trying to get rid of this constant, say gamma hat to the power of minus 2 over n, which is equal to really sigma. So if I have the power of 2 over n with a negative sign, so it becomes sigma hat squared over sigma omega hat squared. Right? Okay, so what is sigma hat squared? So we obtained it before, it's right here. Okay. So this is going to be 1 over n summation j from 1 to b, I from 1 to n sub j, xij minus x bar squared, that is sigma hat squared, and sigma omega squared is something we have just computed right here. So it's 1 over n summation j from 1 to b, I from 1 to n sub j, xij minus xj bar squared. So you can cancel j and j, and we have this one. So we want to see a large value of this one, but at this point, we'll see that this is really, this can really be written as something interesting. So up to this, we are getting some large, we want to get the large value, and large value would mean that we can reject H0 in favor of H1. That means we can conclude that not all the means are same. So the means are different. So at least 2 of the means are different. Okay, so now let's see this a little bit. So let's we will be defining a couple of terms. So total sum of squares, define the total sum of squares, which is given by SS. And this is given by what we have. Summation xij minus x bar squared, and I from 1 to n sub j, j from 1 to b. That's the total sum of squares. We'll denote it by SS, or total SS. Now we'll be defining something called and let's call this by the notation Q also. And now we'll be defining the sum of squares due to error. So sum of squares due to error, which is SSE, and we'll be defining this as xij minus xj bar squared, I from 1 to n sub j, and j from 1 to b. It says that in each group, remember the first example that we're doing? So there are a bunch of machines. So for each machine, there are some variations due to that person. So it's basically the error due to the person. Okay, some squares due to error due to that person. So it's the SSE. Okay, another way to write this as Q3. Yes, all these are different notations. So I can write is S or Q or SSE or Q3. And finally, sum of errors, sum of squares between groups. Remember the examples for the machine. So for each machine, it's making a different error compared to the general mean. So that is captured by this one, and that is given by this number, j from 1 to b and n sub j xj bar minus x bar squared. And we call it Q4. So Q4. Another way. So SSB or Q4. Now, let's look at the last expression right here. So let's call this by name, star. So in star, page 9. So that is my page 9 in the note. What we really have is gamma to, let's, okay, even before doing that, so let's simply, let's try to understand this, and then we'll connect this to star. So what is Q? So Q is really j from 1 to b, I from 1 to nj, xij minus x bar squared, right? I can write this as j from 1 to b, I from 1 to n sub j, xij minus xj bar plus xj bar minus x bar and squared. So I added and subtracted x sub j. So it gives me the following terms. So if I just FOIL it out, so j from 1 to b, I from 1 to nj. So first we have the square of this one. Then I have the square of this one, j from 1 to b, I from 1 to n sub j, xj bar minus x bar squared. And finally, I have twice of the cross term, j from 1 to b, I from 1 to n sub j, xij minus xj bar, xj bar minus x bar. That's the cross term. Okay, now it's very easy to see the cross term is 0. So let's quickly show it. So next page. Will show that this is 0. So, and I can even write this as an aside. Aside to show j from 1 to b, I from 1 to n sub j, xij minus xj bar minus x bar, and we'll show it's 0. Let's FOIL it out. So it's going to be j from 1 to b, I from 1 to n sub j. So the first term is xij, xij, and then xj bar minus xij, x bar minus xj bar squared plus xj bar, x bar. Okay. Now when I take the summation, so this is a summation on j only, so it becomes j from 1 to b xj bar, and then I have summation I from 1 to n sub j xij. Then the second term, so x bar is a constant, so x bar summation j from 1 to b I from 1 to n sub j xij, minus for the third term, well, it's on j only, so the I term will be just giving you nj. So j from 1 to b n sub j xj bar squared, because it's a summation on j only. So when you're taking the summation I from 1 to nj, that is giving you n sub j. And finally, the last term, which is plus x bar summation. So this is the summation on j again. I terms will give you nj. So j from 1 to b n sub j xj bar. Okay. We're almost done. Just observe that I can write this one as n xj bar. Right? And I can write this one too. So here is really, or let's take a part of it. So say this one, I can write this one, this part to be nj xj bar, sum over I. Right? So this is really, so this should be nj. So it's j from 1 to b. We have n sub j xj bar squared minus x bar summation j from 1 to b nj xj bar minus j from 1 to b nj xj bar squared plus x bar summation j from 1 to b nj xj bar. And you see that all these terms are canceling, so it's 0. So this shows that the term that we are mentioning here. Okay. Also this term, look at this term. So this is an summation over I. So this is really, it's independent of I. So it becomes j from 1 to b, I from 1 to n sub j, xij minus xj bar squared plus, I assume that I already proved this is 0. And this is going to be j from 1 to b nj xj bar minus x bar squared. So we, in the next page, we have seen this 0. Okay, so the last term is this one. Okay. Now, if you recall, this is our Q3, and this is our Q4. We have defined it right here. Q3, Q4. So this Q is really broken in two parts, Q3 and Q4. So hence, we found that Q is really Q3 plus Q4. Okay. Very good. So we are almost close to have the derivation. So now let's go back to star. So star on page 9. my note. So it's right here. So basically it says this number is it's essentially Q Q over Q3, right? So this is Q3. So with bar it's Q3. So it's Q over Q3. So we can write this as this gamma hat minus 2 over n is really Q over Q3. And Q is just, now we have proved to be Q3 plus Q4 over Q3, which is 1 over Q4 over Q3, right? So the test rejects H0 if Q4 over Q3 is too large. Okay. This one is just a constant. Now the final thing we'll be doing is we'll be trying to understand this quantity. Now let's consider this quantity Q3 over Q4. Sorry, but Q4 over Q3 I can write this in terms of I mean Q. So I mean let's see what this Q4 is. Okay, so we will try to understand Q3 and Q4. Okay. Let's read. Now, if I compute Q3, where is Q3? Over sigma squared. This quantity. So let's write this Q3 over sigma squared one more time. According to our definition, so this is, I can just write this in the following way. J from 1 to B, and let's put a sigma squared here. Sigma squared I from 1 to n sub j. In the case of random variables, say xij minus xj bar squared. Okay. So in case of, so we are just replacing the numbers by the distribution because now we are discussing the distribution. Okay. Now let's look at this quantity. So this is basically the sample variance for this particular bucket. So this is nothing but, I can write this as, if I just show you the first one. So I'm going to use this result. Right. So this is nothing but the sample variance. So this is, I can write this this quantity I from 1 to nj xij minus xj bar squared is really nj minus 1 s squared, the sample variance. For that particular group, for group J. Okay. And each group will have the standard deviation sigma. So that means nj minus 1 s, let's write it sj, sj squared over sigma squared. It also follows a chi squared distribution with nj minus 1 by this result. And hence, and all these are independent. Therefore, also samples are independent. Which implies this Q3 over sigma squared really follows a chi-square distribution with degrees of freedom, where I just add up j from 1 to b nj minus 1. So that is really chi-squared. And if I sum this, it's n minus b. So this Q3 minus sigma squared, it follows a chi-square distribution. Okay. So that is the first observation. And then the second observation is, let's look at the other one. Now, of course, I can write this, this Q we have written similarly. It is easy to show that the Q that we defined before over sigma square, that also follows a chi-square distribution. And in this case, its degrees of freedom is n minus 1. Okay, just check it yourself. So it's basically the same proof. Okay, now the last part, 13. Now let us look at this one. This is a little subtle, so please follow this last part carefully. What we have is the following. So we know that Q is a particular chi-square and Q3 is a particular chi-square, right? Now, note that this x bar j is independent of say sum of squares like this one, I from 1 to nj x ij minus xj bar squared. Why? Because of the, once again, of the first theorem that we showed in class today. I'm trying to find it. Yeah, it's right here. So x bar and s squared are independent. So since x bar and s squared are independent, Student's theorem. Now, what is the use of this observation? So that means by the independence of samples, so this xj bar or j is independent of Q3 as well, because Q3 is nothing but the sum of this one, right? So Q3, what is Q3? So Q3, which is just the sum of j from 1 to b, I from 1 to n sub j, xij minus xj bar squared, right? Okay. Now, but x bar, that is the grand mean. And that can be written as, say, nj xj bar j from 1 to b. So it's a function of n independent random variables, which are independent to Q3, So that means it's independent by the previous analysis of Q3. All right, once again. So first of all, we observe that xj bar is independent to this one because of the previous student's theorem, right? Then that means we have xj bar is independent of the sum of all this, that is Q3. And now x bar, which is the grand mean, which is the combination of all such xj bars. So that means this is independent of Q3 as well, right? So therefore, my final conclusion is Q4, which is j from 1 to b, nj, xj bar minus x bar squared. So this quantity, everything here is independent of Q3. So we have seen xj bars are independent of Q3, and this is independent of Q3. That's a very, very important step. Okay. Now let's look at this. This is important because of the following. Now we have Q equals Q3 plus Q4, right? So that means Q over sigma squared equals Q3 over sigma squared plus Q4 over sigma squared. What do you know about Q over sigma squared? It follows a chi-square distribution. Like here, it's with n minus 1 degrees of freedom. It follows a chi-square distribution with n minus b degrees of freedom. And what we know is Q4 and Q3 are independent. That's what we've shown here. Okay. That's why we spend so much time on this one. Hence, what does it mean? So this is a sum of like two distributions. So and then it can be shown then that therefore, so Q4 over sigma square, it satisfies a chi-squared where the degrees of freedom is the difference between this and this. So it's a difference between n minus 1 and n minus b, which is b minus 1. So it's chi-squared b minus 1. So that is the distribution for Q4. Okay. So we have these two nice distributions. Now let's consider this quantity. So we have this Q4 over sigma squared, it's chi-squared, so divide by b minus 1. And then we have Q3 over sigma squared, divide by n minus b. Chi-squared divided by degrees of freedom, chi-squared divided by degrees of freedom. So we know that this follows an F distribution with b minus 1 and n minus b. We have seen it once again at the very first thing. So today in the class, this is one of the very first things that we did. So if we have two independent, Q4 and Q3 are independent, we have seen. And so then the two independent chi-square divided by its degrees of freedom, that is F distribution. So what we found is really Q4 divided b minus 1, Q3 divided by n minus b, it follows the F distribution. Now going back to this quantity, so let's see. So I can write this, therefore, gamma hat, I can even write this as F. So F equals to this one. So gamma hat of minus 2 over n, we found it as 1 plus Q4 over Q3. So this is really, so Q4 over Q3 is 1 plus, so b minus 1 over n minus bf. Right? So this quantity, if it's high, So if it's so if it has higher values, then it decline will reject null hypothesis. So that means if f is um, large or too large, then we reject H0 in favor of H1. So that is the practice, and then that is how we'll be doing it. Okay, so today we understood everything theoretically. This is a little intense mathematical analysis, but this is useful. So one more thing, one more thing before I forget. There are some technical terms which we use in association. This is associated to this particular analysis. Let me just mention it so that we can easily solve some of the examples. So this quantity that we obtained here, it's sometimes called this Q4 over B minus 1. Note our names. So this Q4 over B minus 1 is sometimes called the MSB, which is, in other words, it's mean square between groups. And this Q3 over N minus B, it's called the MSW, which is mean square within groups. Okay. So essentially, this F, the quantity F that we wrote here, so F is the quotient of the MSB and MSW. So let me just write it. So F is really, it's MSB by MSW. So under null hypothesis, under H0, it follows F distribution with degrees of freedom as we mentioned before. It's D minus 1 and minus B. So if the observed value of the statistic equals or exceeds the theoretical F value, at a specific level of significance, we reject H0 and conclude that all the population means are not equal. On the other hand, if the observed value of this F, if the observed value of the F is less than the theoretical value we conclude, we accept a 0 and conclude that all the population, that means among the groups, population means may be considered to be equal. That's a complete test. Okay. So today we have approached this from a theoretical point of view. So next class will be considering some examples, and we'll see how this can be used in practice. Now, when we compute this in practice, we'll be making our computations a little simpler by using a lot of different things. So you'll see that we'll be using all these terms, but in a little different context. So the computations are a little different compared to what we did. But what we did today is we theoretically understood what this test is, like how this one-way ANOVA is working. So how is that related to the this F distribution? Okay. So that's all about it. So next time we'll do some example. Okay. So thank you very much.